Hello. So I'm starting the recording of this PMRF live session. There are no students in the class currently, so I'll just record this session as it is and upload it in YouTube, and then anybody can watch after that. So in this last class, what we had done was that we had covered Bose-Einstein statistics and Fermi-Dirac statistics. So we had studied ideal quantum gases. Basically, we had taken ideal quantum gases in 3 dimensions and they were considered to be free particles. So their energy was proportional to p square. And in the quantum sense, p is equal to h cross k, where k is the wave number. So so the energy was of each particle was equal to h cross square k square by 2m, like that. And then we proceeded forward and then we obtained expressions for the grand potential function and sorry, the grand partition function. From that, we were able to calculate the particle number densities, the internal energies of both Bose and Fermi gases, and other quantities of interest like grand potential function and so on. And then we had done high temperature and low temperature expansions. So we saw that in the high temperature limit, both the Bose and Fermi gas, they give the same statistics as that of a classical ideal gas in 3 dimensions. And in the low temperature limit, their statistics are very different. So for your Fermi gas, we had this because of the degeneracy of fermions that only one single fermion can occupy a given energy level at one time. So we had that degeneracy in case of fermions. And because of that, we had non-zero values of specific heat at T equal to 0, that is at 0 temperature. The internal energy was non-zero at T equal to 0. Sorry, not specific, the internal energy and the pressure, they were non-zero at T equal to 0. And this non-zero value of pressure is known as degeneracy pressure. And I had explained the importance of degeneracy pressure in the context of astrophysical systems like stars, for example, electron stars and neutron stars and so on. And then we had studied the low temperature characteristics of Bose gases as well. And we had seen that there is a macroscopic occupation of the lowest energy levels below a certain critical temperature. And this is the critical temperature for Bose-Einstein condensation. This phenomenon itself is known as Bose-Einstein condensation. And we saw that this temperature depends upon the density of the gas we are considering. All right. So in today's class, I'll be solving a few problems based on Bose-Einstein and Fermi-Dirac statistics and their applications to various real-world phenomena, real-world systems. Okay. So there are basically 3 kinds of problems I'll solve in today's class. The first one is a Bose gas and a Fermi gas in d dimensions, and any having a generalized form of energy. So in the previous class, we considered the energy to go as p square, that is, they were only free particles. But instead of p square, if we have something like p to the power of s, where s can be any integer or a fraction. So what do we do in that case? And also, if we have dimensions other than d equal to 3, then do we observe Bose-Einstein condensation or not? So that is the first problem that we are going to address. The second thing which we will do is that we will study Pauli paramagnetism and ferromagnetism from the context of Fermi-Dirac statistics, because we'll see how fermions can give right, how the from Fermi gases we can derive the Curie's law of magnetic paramagnetic susceptibility. And we will also see how ferromagnetism emerges from a system of fermions which interact with each other. Okay. And finally, we will also study about relativistic Bose gases in d dimensions. And the relativistic Fermi gases in d dimensions I'll cover in the next class because that has to do with Chandrasekhar limit, which I will speak about in more detail. Okay, so I will start sharing my screen now. Yes, okay. Okay, so here is the first question. It's a generalized quantum ideal gas. So consider there is a gas of non-interacting identical spinless quantum particles whose energy spectrum epsilon is equal to mod of p by h cross to the power of s. S is any number. It's a general value not equal to 2 as we had earlier. And it is contained in a box of volume V in d dimensions. Okay, so the first thing which we have to calculate is the grand potential function. This is something, okay, so grand potential function zeta xi, or yeah, xi eta, which is equal to minus kBT ln q eta, and the density as a function of the chemical potential. So how do we proceed in this case? We proceed in the same manner as we had done earlier for the quantum gases in 3 dimensions. Okay, so this is in d dimensions instead of 3. So this is the expression for the energy which was given to us, since P by H cross is equal to K. This is K to the power of S, and V is the volume of the box. Now the grand partition function can be written in this manner. So Q, the grand partition function, is a summation over capital N going from 0 to infinity e to the power beta mu n, and summation over small nj's e to the power minus beta, summation over j nj epsilon j, where beta is equal to 1 by kbt. Capital N is summation over j nj. So nj here is basically the number of particles in a given energy level, which is denoted by j. The energy of the jth energy level is epsilon j. And if I sum over all the energy levels, I get the total number of particles. Okay, so summing over all j, I get total number of particles. And basically summation over all j nj epsilon j gives me the total energy. So this entire thing over here is known as the grand partition function. So basically a grand partition function, it's nothing but the partition function which we had earlier. That is, it calculates, counts across the number of microstates. How does it do that? Basically, it sums over all combinations of nj, and then there is the summation of capital N going from 0 to infinity. So as you can see, the system here is allowed to exchange particles with the reservoir. That's why N is not a fixed quantity here. On the other hand, the fixed quantity is the chemical potential, that is mu. Okay. So this is only the summation notation over here we have is for discrete energy levels, as we have seen in the previous class. If we have continuous energy levels, we will replace the sum by an integration. So that's what we'll do as we proceed onwards. Okay, so for fermions, you know that there can only be at most one fermion in a given energy level. So Nj can either be 0 or 1. All right. So what happens is that if nj is either 0 or 1, then I can replace this summation by a product over j. Okay, so that is what I've done over here. A summation in the exponential can be replaced by a product over these energy levels here. So this is product of j e to the power beta minus epsilon j nj, and this summation over n. So I can actually remove the summation by so the summation gets removed because of the summation of capital N going from 0 to infinity. So that is how the constraint on this nj gets removed. And so then I have a product over all the energy levels into the summation over occupation number, that is nj going from 0 to 1, of this quantity e to the power beta into mu minus epsilon j into nj. Okay, so if I do the summation for the, then nj simply has two values. So I get 1 for nj equal to 0, and for nj equal to 1, I get this quantity. And so this is a product over all energy levels j, 1 plus e to the power beta into mu minus epsilon j. Okay, so similarly for bosons, nj can take any value. It may not necessarily be 0 or 1. So simply this becomes a product over j and a summation over nj, where nj goes from 0 to infinity. Okay, so if nj goes from 0 to infinity, then this is basically a sum over an infinite GP series. Why infinity? Because I have my capital N going to infinity. Okay, so since my total number of particles can be infinity, I take the sum nj going from 0 to infinity, and then I take a product over all the energy levels. Okay, so since this is a sum of an infinite GP series, so this becomes 1 by 1 minus e to the power of this ratio e to the power beta mu minus epsilon j. Okay, so basically this 1 over thing, I write it as to the power of minus 1 over here. So I can write a general expression for this grand potential function, which is capital Q of small q. So, product is equal to product over j, 1 plus small q into e to the power beta into mu minus epsilon j, whole raised to the power q. And if I put q equal to 1, I get fermions. If I put q equal to minus 1, I get bosons. So this was something which we had covered in the previous class. Now comes the different part. In the previous class, we had only considered three dimensions. Now we consider any general d dimensions. So what do we do for d dimensions? We replace the summation. Okay, by the way, the summation turns into a log. If I mean, so its product turns into a summation if I take a log. So the grand potential is equal to minus kbt ln q. So then the product turns into the summation like this. And then I replace the summation by an integral. Okay. So the summation of over all energy levels gets replaced by this d-dimensional integral in position and momentum space. Okay. So there are d integrals over the d position coordinates and there are d momentum coordinates. So that's why there are two integrals over here. All right. So if I do the position integral first, then I will get nothing but the volume of the box, the volume in which my particles are constrained. So I get V, and this integral, the momentum integral, I normalize each of these wave numbers by 2 pi. That's why this factor of 2 pi to the power of d comes out in the denominator. So this turns into V by 2 pi to the power of d integral over all the momentum coordinates. Okay, where the momentum coordinates are all normalized by 2 pi. Now, how do I do ddk? So since my momentum quantum numbers, they are spherically symmetric in the momentum space for the case which we have over here. So there is no restriction on the total on the wave vector as such. It's isotropic in the wave vector space. That is why I use the spherical symmetry. So this integral over ddk, this is nothing but st into integration k to the power d minus 1 dk, where st is the solid angle in d dimensions. So for example, in three dimensions, this would be d3k would end up becoming 4 pi k square dk, right? So 4 pi is the solid angle, k square is basically k to the power 3 minus 1. So that is how this term comes in. So an important message is that any summation over the energy levels in d dimensions can be replaced by this integral if I consider the energy levels to be very closely spaced. Okay. And the solid angle in d dimensions is given by this formula 2 pi to the power of d by 2 divided by d by 2 minus 1 factorial. All right. So if I consider now, if I go back to this expression of log of q, then if I replace the summation by the integral, this thing becomes q into vst by 2 pi to the power d, q to the power d minus 1 log of 1 plus q e to the power b into beta into mu minus epsilon into dk, where epsilon is now a continuous number instead of the discrete value which we had earlier, that is epsilon j. Epsilon is, epsilon is now k to the power s, and k varies continuously. Okay. Now we make the substitution z equal to e to the power beta mu as we had done earlier. And we also make the substitution that x equal to beta k to the power s. So what does that do for us? Beta k to the power s is basically beta epsilon. So then k becomes x by beta to the power of 1 by s. And then dx is equal to s beta k to the power s minus 1 into dk. So then dk is equal to dx by s beta into k to the power of 1 minus s. All right. So dk is equal to 1 by s beta, x by beta raised to the power 1 minus s by s into dx. Okay. So then I have log of q is equal to small q into v by 2 pi to the power of d st, integration dx by s beta, x by beta 1 minus s divided by s, x by beta to the power of d minus 1 by s into log of this quantity. So I basically get this if I substitute all these results into this integration over here. Okay, now if I simplify this further, then what I get is q into vst by 2 pi to the power d, beta to the power of minus d by s integration from 0 to infinity dx x to the power of d by s minus 1 log of 1 plus qz e to the power minus x. Now I do an integration by parts. So if I do that, then first I integrate over x and I differentiate over log of this quantity. So integral over x would give me x to the power of d by s divided by d by s. So this s and s get cancelled out. And the first term becomes 0 because x goes to 0 at, so this log goes to 0 at x equal to infinity, and at x equal to 0, this entire thing is equal to 0. So the first term becomes 0, and what I have is only the second term if I do the integration. All right. So then a log of q is basically this quantity, which is integral of dx x to the power d by s z e to the power minus x, 1 plus q z e to the power minus x. By the way, there should be a plus sign over here, I think. Okay. So once that is done, then I can rewrite this integral in this particular form, that is integration from 0 to infinity dx x to the power of d by s z inverse e to the power x plus q. And this is nothing but the familiar form of the function fmq, which I had defined in the previous class, where fmq is defined as 1 by gamma m into this integral over dx x to the power m minus 1 by z to the power minus 1 ex e to the power x plus q. Okay, so if I compare this expression with this expression over here, then this is nothing but gamma of d by s plus 1 into f of fq d by s plus 1 of z. So this is what I've written over here. So ln q is, this is a plus sign, vst by 2 pi to the power d, beta to the power of minus d by s divided by d, gamma d by s plus 1, f to the f of d by s plus 1 z. Okay, so we get an expression for log of q, and from that we can directly calculate this grand potential function, which is minus kbt into this thing, or minus 1 by beta into this thing. Okay, so this will be a plus sign over here. So actually there will be a negative sign in front of this expression over here, but the rest of this is correct. Okay, so this is the grand potential function that we get. And now if I look at the total number of particles, then capital N is summation over j 1 by 1 plus q into e to the power beta into mu minus epsilon j. This is what we had got for the discrete case. And if I look at this discrete summation over here of log x, yeah, where is this expression? Yes, so this is the discrete sum of over log x which I get if I do the summation. Okay, so if I look at this discrete summation, then my total number of particles is nothing but del del beta u of ln q. All right. So I can use the chain rule and write it as del del z of ln q into del z del beta u. And since z is nothing but e to the power beta u, so this becomes e to the power beta u over here, beta mu over here. Okay. So this is z into del del z of ln q. Now, what is del del z of ln q? Del del z of ln q is basically del del z of this expression over here. Okay, or if I go further up, then it is the del del z of this expression. So if I take a derivative with respect to z, then log of this quantity is the only z dependent term over here. So this becomes 1 by 1 plus qz e to the power minus x into q e to the power minus x, e to the power minus x, yes. So that's what I get over here if I take the derivative. So q by z comes out, and then I have x to the power of d by s minus 1 in the numerator divided by z by minus 1 to the power x plus q. Okay, and if you look at this, this is nothing but gamma d by s into f d by s of z. Okay, if I look at this expression over here, so that's what I've written over here. So if I substitute over here, then n is z into del del z of ln q. So this, I put the entire expression of ln q over here now. So this becomes v into st by 2 pi to the power d, kbt to the power of d by s, gamma d by s into f d by s of z. Okay, so the number density is total number by volume, which is st by 2 pi to the power d, beta to the power of minus t by s, gamma d by s into f d by s of z. All right, so this is how we can get expressions for the number density of ideal quantum gas in d dimensions. Or yeah, generalized quantum gas in d dimensions. All right, so this solves part A. Now what do I have in part B? In part B, I have to find the ratio PV by E and compare it with the classical result that we had obtained previously. Okay, so you know that beta PV is nothing but my ln q. Okay, so PV, it's nothing but minus ln q actually. So PV becomes equal to this quantity over here, and also the internal energy is given. So this is what I get if I replace log q by its formula which I had obtained earlier over here. Okay, Yes, so if I replace ln q by this formula, then I get the expression for beta PV. Okay, so yeah, so also the internal energy can be written in this manner. So it is summation over J, summation over energy levels epsilon J by the occupation probability into the occupation probability. Yep. So this is equal to minus of del beta of ln q. This directly follows from the expression of ln q which we had earlier. Okay. So if I do this, then you will find that ln q, it depends on beta via this quantity over here, right? So then if I take the derivative, then it simply becomes beta to the power of minus d by s minus 1. So that's what I get in the numerator, beta to the power minus d by s minus 1. So minus 1 factor, because I have the minus 1 factor, so I have the beta over here, d by s into ln q itself. All right. And ln q is nothing but beta p. Ln q is right. So 1 by beta ln q is nothing but PV. So this is equal to d by s into PV. So then I have PV by E is equal to S by D. Okay. So this is the same as the classical result which we had earlier. How? So if I put D equal to 3 and S equal to 2, then I get PV is equal to 2 by 3E, which is what we had obtained for a three-dimensional classical ideal gas. Okay, now going to the third part. Um, yes. So in the third part, we have to, for fermions, we have to calculate the dependence of E by N and P on the density small n equal to capital N by V at zero temperature. Okay. So basically, I have to now consider the low temperature limit for fermions. Right, and I have to calculate the dependence of E by N and P on the number density itself. So how do I go about that? So for fermions, we know that chemical potential is almost equal to the Fermi level as T goes to 0. This is something which we had covered in the last class. So then 1 by Z inverse e to the power x plus q can be written as 1 by e to the power beta epsilon minus epsilon f plus 1. I have put q equal to 1 because it's a fermion. Okay, now in the limit of t going to 0, this function, this can be replaced by the step function, right? This is also what we had seen in the previous class. Why? Because in the limit of t going to 0, beta becomes a very large quantity. So for all energy epsilon, which is smaller than the Fermi level, this quantity becomes 0. So this is equal to 1. And if epsilon is greater than epsilon f, this quantity becomes infinitely large, which is why this is 0. So this can be replaced by a step function theta of epsilon f minus epsilon, where theta of x is 1 if x is greater than 0 and it equal to 0 if x is less than 0. So this is something which we had done earlier. So now we use this fact to evaluate f of m. So fm of z is given by 1 by gamma m 0 to infinity px x to the power m minus 1 divided by this quantity in the limit of t going to 0. Now since this is a step function, so you will see, and the x is nothing but beta epsilon, right? So this is nothing but e to the power x minus beta epsilon f. Okay, so this, since this thing is a step function in the limit of beta going to infinity, so you will see that for x values of x which are larger than beta epsilon f, this integral is 0. And for values which are smaller, this integral is 1. So that's what we have done. So we have replaced this quantity by 1 and we have restricted the limit of this integral to go from 0 to beta epsilon f. Why? Because anything beyond that is equal to 0. Okay, and if we do that, then the evaluation of f of mz becomes easy. So fm of z is nothing but, if I do this integral, then it is almost equal to 1 by m gamma m beta epsilon f to the power of m. Right, so we get this expression of fm in the limit of t going to 0 in the small temperature limit. Now I have to find the dependence of E by N and P on the number density. So what I do is that I express these quantities in this particular limit of t going to 0. So I have over here for this quantity energy that F d by S plus 1 of Z. I can replace by this expression in the limit of t going to 0. So f d by s plus 1 of z is approximately equal to 1 by d by s plus 1 into gamma of d by s plus 1, and in the numerator I have beta epsilon f to the power of d by s plus 1. If I put this expression over here, then the two gamma functions cancel out, and what I get is vst by 2 pi to the power of d 1 by s into 1 by d by s plus 1 into epsilon f to the power of d by s plus 1. Okay, so this is how it depends on epsilon f. Similarly, for the expression of PV, so PV was given by this expression. Again, I have this factor of f of d by s plus 1 over here. If I replace it, then I get this expression for PV. And similarly for small n, here is the expression for small n. So for small n, it was gamma d by s and f d by s instead of d by s plus 1. Okay, so I again replace this particular expression over here, and this beta d by s factor also cancels out, and then I get small n is equal to st by 2 pi to the power of d s by d into epsilon f to the power of d by s. Okay, so this is small n. So what does e by capital N become? E by capital N is nothing but e by small n into v. So I divide this expression by this expression multiplied by v. So v s d by 2 pi to the power of d will cancel out, as you can see over here, and this thing turns out to be of the order of epsilon f. Okay, because of different factors cancelling out, and this goes as epsilon f, sorry, it's of the order of epsilon f to the power of d by s plus 1. And we know that epsilon f to the power of d by s plus 1 scales as n to the power of s by d plus 1. Okay. Okay, there's a mistake over here. This d by s won't be here actually. So if I divide e by n, then the d by s factors cancel out, and I have only epsilon f in the denominator. So actually, this won't be d by s plus 1. This will simply be epsilon f. Okay, and epsilon f scales as n to the power of s by d if you invert this expression. And similarly, if I write an expression for capital P in terms of number density, so this was the expression for number density which I had over here. So n was proportional to epsilon f to the power of d by s, and epsilon f is proportional to s by d. So if I replace epsilon f by s by d, then I get nothing but p going proportional to n to the power of s by d plus 1. So that is why E is proportional to S by T and P is proportional to S by T plus 1. So for bosons, I have to now find the dimension below which there is no Bose-Einstein condensation. So how do I find the critical dimension for Bose-Einstein condensation? So we look at the expression for number density and we calculate, and we know that this F minus, which is the F function for bosons, it's a monotonically increasing function of Z, and it is bounded at the top by Z equal to 1. So beyond Z equal to 1, this function diverges, right? So Z equal to 1 is the maximum value which bounds this function. Now I have to, because Z goes from 0 to 1. Okay, so now I have to see whether there exists, whether this function f of minus, it diverges at Z equal to 1 or not. So if the function f diverges, then there will always be a value of density which is less than infinite, less than the maximum density of excited states. And if the function diverges, then the maximum density of excited states is basically infinity. So all states will always be excited in this case, and there will be no Bose-Einstein condensation. On the other hand, if f minus at z equal to 1 is a finite quantity, then I can have a value of density which exceeds this maximum number. So in that case, Bose-Einstein condensation can occur, and we can find a critical temperature for the same thing. So this is what I've done over here. So I've considered the maximum value of Z, and I've evaluated the density at this maximum value. So at Z equal to 1, the density of excited states can be written by this formula. So as I had mentioned earlier, you have this factor of f d by s of 1 over here. minus represents bosons. Okay, now I have to now see for what values of d by s this value is a finite quantity. So for those values of d and s for which this is a finite quantity, for them we'll have Bose-Einstein condensation and otherwise we will not. So let us take a look at this. So f d by s of 1 can be written in terms of this particular expression. So if we look at this integral, so we'll see that for all d and s, this integral tends to 0 as x goes to infinity. Why? Because this is e to the power infinity in the denominator and it goes to 0 at infinity. Now, this can diverge only in the limit of x going to 0. So in order to check the limit at x going to 0, we consider this integral only at within a small range of 0, that is 0 to epsilon, where epsilon is a very small quantity. And in the limit of x going to 0, we Taylor expand the exponential, that is e to the power x can be written as 1 plus x squared and so on. We retain only up to the first order term, that is x. So this becomes 1 plus x minus 1, that is x. So that's why I have x to the power d by s minus 2. So now I look at this integral 0 to epsilon dx x to the power d by s minus 2, where epsilon is a very small quantity. So as you will see over here, this integral, this will diverge if d by s minus 2 is greater than minus 1, right? This is obvious. Or in other words, if d is greater than 0. So the condition that for which we will have no Bose-Einstein condensation is that if d is greater than 0. So if d is less than or equal to 0, we will have Bose-Einstein condensation. Uh, Sorry, it actually should not be d greater than s, but it should be d greater than or equal to x, because even if d is equal to s, then this integral diverges logarithmically. Okay, so only if d is less than s, then we'll have Bose-Einstein condensation. Otherwise, we won't have it. So, for example, for a two-dimensional Bose gas, ideal Bose gas, we had d equal to 0 and s equals to 2 because epsilon equal to p square. So if that is the case, then there will be no Bose-Einstein condensation because this integral will diverge, right? So that is why for a two-dimensional Bose gas, we don't have Bose-Einstein condensation. So this is an important result which we get by solving this problem. Okay. So now that this problem is done, let us move on to the next one. The next one is about polyparamagnetism, and polyparamagnetism basically comes around due to the spins of unpaired electrons. Basically, it comes about because of the spin magnetic moments of electrons themselves. Okay. So how does that come about? That's what we'll see in this problem. So we have to calculate the contribution of electron spin to its magnetic susceptibility in the following manner. We consider non-interacting electrons, each of which are subject to a Hamiltonian of the form given over here as p squared by 2m minus mu naught sigma dot b. Okay, where mu naught is E h cross by 2mc and the eigenvalues of sigma dot b are plus minus b. So basically, an electron spin can either align with the magnetic field or antiparallel to the magnetic field. Okay, so if it aligns antiparallel to the magnetic field, then the eigenvalue is minus b. If it aligns parallel to the magnetic field, the eigenvalue is plus b. And then, so the first thing that we have to do over here is that we have to calculate the grand potential. So since we are given the Hamiltonian, we can easily do it. And one more thing we have to keep in mind is that it is a system of fermions. Okay, so we proceed accordingly. So the total energy of this electron gas is given in this manner: summation over all momenta p E of np plus np minus, where np plus denotes the number of electrons which are upspin. So by upspin, I mean the electrons which are aligned parallel to the magnetic field, and by downspin, I mean the electrons which are antiparallel to the magnetic field. So the upspin electrons I denote by Np plus and the downspin electrons by Np minus. So Np plus and Np minus are the number of electrons with momentum p which have upspins and downspins respectively. Okay, so the total energy of the system can be written as a combination of these two types of electrons. So this is the contribution which comes from the upspin electrons, and this is the contribution which comes from the downspin electrons. Okay, so as you can see over here, for upspin electrons, sigma dot b is equal to b. So that is why this thing is minus mu naught b. And for downspin electrons, sigma dot b is minus b. So therefore, this is plus mu naught into b. and then I rearrange the summation and write it in this format. Okay, now I go on to the calculation of the grand partition function. So this is the formula which we saw earlier. Here the summation is over all different configurations of np plus and np minus. Okay, and the summation over p of np plus np minus gives me the total number of electrons that are there in my system. So what I do is that I can basically, since this is basically a summation in the numerator, summation in the exponential itself, because I'm summing over energy levels, I can replace this by a product. That removes the constraint on the number of particles from here. So if I can write n in terms of this summation, and that this energy can also be written in terms of the summation over all energy levels, because if I replace it by a product over here, so this is a product over all energy levels P, and summation over the possible values which NPs can take into exponential of beta mu into NP plus NP minus coming from this thing, minus beta into P square by 2m into NP plus NP minus coming from this thing over here, and minus beta mu naught B into NP minus plus NP plus, which comes from this term. Okay, now what are the possible values that NP plus and NP minus can take? They can either be 0 or 1. So there are basically four combinations which come out from this summation. One combination is NP plus equal to NP minus equal to 0. Another combination is NP plus equal to 0, NP minus equal to 1. Third combination is NP plus equal to 1, NP minus equal to 0. And the fourth combination is that both NP plus and NP minus are 1. So as you can see, all of these represent separate states. Okay, so they all satisfy the constraints of which fermions have. That is, two fermions with the same set of quantum numbers cannot have this. That is, two fermions cannot have the same set of quantum numbers. So this is the thing which satisfies this constraint. Okay. So if I uh, remove the summation then by substituting these combinations of NP plus and NP minus, then I get this expression of Q, where it is written as a product of P into this term multiplied by this term. Okay. So basically this one comes from this first term. Then one factor of exponential of mu minus mu naught B comes from this one of comes from this particular term. Then the factor of epsilon mu plus mu naught B comes from this term, and a factor which is the combination of both comes from this term. Okay, so this can, if I rearrange the terms, then I can write it as the product of these two terms, and they can be written in terms of these two quantities Q naught for simplicity. So this helps us in the ease of notation and also in our subsequent analysis. So Q can be written as Q naught into Q naught as a function of mu plus mu naught B multiply Q naught as a function of mu minus mu naught B, where Q naught as a function of X is nothing but product over P 1 plus exponential of beta into X minus P squared by 2m. So for X equal to mu minus mu naught, I get this term. X equal to mu plus mu naught, I get this term. Okay. So if I take the log of two sides, I get log of Q naught as a function of mu plus mu naught B plus log of Q naught as a function of mu minus mu naught B. Okay. Now I can expand the logarithm. I can substitute for Q naught. Then the product becomes a summation inside a log because it's inside a log. Okay. So then I can write it as a summation over P log of 1 plus exponential of beta mu minus P squared by 2m into e to the power of minus beta mu naught B plus summation over P log of the same quantity multiplied by e to the power of beta mu naught B. So there is a minus beta here and a plus beta here. So this is the only difference between these two terms. Okay. So now what we do is that we replace the summation by integral as we had done earlier. And because P is equal to h cross k can be written as P by h cross. So then 1 by 2 pi cube d3k can be written as 1 by 2 pi h cross cube into d3p. Right. So that is why log of q can be written as v by 2 pi h cross cube into, this is the integral which comes from the first summation, because you see all these factors directly follow from here. Z is equal to e to the power of beta mu, and you have this factor of e to the power minus beta mu naught b over here. And this integral comes from this second summation over here, where you have this factor of e to the power beta into mu naught b. Okay. Now we again make the substitution that d3p is equal to 4 pi p squared dp from spherical symmetry. And we make the substitution that x is equal to beta p squared by 2m. So then p is equal to 2mx divided by beta. Then if we replace these quantities here, we have log cube to be given by v by h cross cube into 4 pi m by beta into root over 2m by beta. Then we have these two integrals with, and they are similar to each other. The only difference is in these two factors of e to the power of beta mu naught b and e to the power, okay, e to the minus beta mu naught b and e to the power plus beta mu naught b over here. Okay, so now I would integrate both of these integrals by parts. So let us look at the first integral because the second one will directly follow from the first. So if I integrate by parts, so I integrate over the root over x first, and then the first term becomes equal to 0 at x equal to 0 at infinity, and I'm only left with the second term. All right, and what is the second term? In the second term is nothing but z into x to the power of 3 by 2. Why 3 by 2? Because this 3 by 2 factor comes from integrating x to the power half. E to the power of minus beta mu naught b, there will be a factor of e to the power minus x over here divided by 1 plus e to the power minus x e to the power minus beta mu naught b plus this quantity. Okay, there is a factor of e to the power minus x over here, and here is the factor e to the power plus beta mu naught b. So what I do is that I divide both the numerator and denominator by e to the power minus x into e to the power minus beta mu naught b for the first integral. And for the second integral, I divide the numerator and the denominator by e to the power minus x into e to the power beta mu naught b. And then I arrive at this expression. And this expression will seem familiar to you because this is nothing, this can be written in terms of these f functions. So if I this you have this factor of gamma 5 by 2. This gamma 5 by 2 comes from these prefactors over here, which I had earlier. Okay, and lambda is the thermal de Broglie wavelength, which can be written in, which is equal to h by root over of 2 pi mkbt. Okay, so then if I combine the factor of 1 by gamma 5 by 2 with this integral and this integral, then I can write them in terms of these f functions. So then log of q is nothing but v by lambda q into f5 by 2 z e to the power minus beta mu naught b, and this is f5 by 2 of z e to the power beta mu naught b. So this is how I get the expression for log q, and then the grand potential can be written in this manner by simply writing it as minus kbt ln q. Okay, so now moving on to the second part of the problem. We have to calculate the number densities of the upspin and the downspin electrons. So the number density of upspin electrons is basically n plus by v. So we had seen earlier that n could be written as z into del z of ln q. So if I divide q into q plus and q minus, which I had done earlier, so if you look at this expression, you would see that you can directly read out the values of q plus and q minus from these expressions. Okay, so q plus basically denotes the q for those electrons which are pointing parallel to the magnetic field. So this is the expression for q plus. So q plus is nothing but q of mu minus mu naught b, and q minus is nothing but q naught of mu into q naught of mu plus mu naught b. Okay, so that's what I do over here. So first I have the expression for n of q plus over here. So n plus is nothing but z by v into del z of ln of q plus, and ln of q plus, this will be a minus sign over here. Mu, sorry, no, this is plus sign only. Mu plus mu naught b naught minus p squared by 2m. Okay. So if I take a del z of this expression, then I can write it yet again in terms of these f functions, and you will see that this is nothing but f of 3 by 2. Okay. This simply follows if you take the z derivative of this logarithm over here. Right? So I can write n plus as 1 by lambda cube if I take these prefactors into account properly. into f3 by 2 plus z e to the power of beta mu naught b. And similarly for n minus, I get 1 by lambda cube f3 by 2 z e to the power of minus mu naught into b. So this is how I calculate the number density of electrons pointing up and down. Now, once you know the number density of electrons pointing up and down, you can directly calculate magnetization. Magnetization is the total magnetic moment per unit volume, and magnetic moment is simply obtained by subtracting the is given by the difference between the number of upspin and downspin electrons. Right. So that's what has been asked in the next question, I think. Yes. So in the next question, we have to obtain the expression for magnetization and expand the result for small v. So magnetization, this is the total magnetic moment, in fact, which is equal to mu naught into n plus minus n minus. Okay. So we had n plus over here, and n plus is capital N plus is small n plus into v. Capital N minus is small n minus into v. If I substitute over here, then this is mu naught v by lambda cube f3 by 2 z e to the power of uh, beta mu naught b minus f3 by 2 z e to the power of minus beta mu naught b. So this is the expression for the total magnetic moment. Now I have to find out what it is in the limit of magnetic field going to 0. So for a small value of magnetic field B, what I can do is that I can approximate this f function in this following manner. So f3 by 2 set e to the power of plus minus beta mu naught b. So since b is very small, I can expand the exponential in a Taylor series. So I write the exponential as 1 plus minus beta mu naught b, and I neglect all the higher order terms. Okay. So f of this quantity and the limit of very small b, I make yet again another Taylor expansion of this entire function. So if I do that, I get, and this Taylor expansion is about z. Okay. So if I do the Taylor expansion, I get f3 by 2 of z plus minus, uh, what is this? This is f3 by 2 of z plus minus z into beta mu naught b del del z of f3 by 2 of z, right? So this is what the Taylor expansion gives me. Now I make use of this formula that z into del del z of f n z is nothing but f n minus 1 of z. This is something which we had done in the previous class as well. So if I replace z del z of f n z in this expression by this formula, then the left hand side is f3 by 2 of z plus minus beta mu naught b f half of z. Okay, so then my magnetization, if I replace f3 by 2 of these two quantities by these two expressions over here, one for plus and one for minus. So this term cancels out, and then magnetization becomes nothing but 2 into mu naught square V by lambda cube into beta B F half of Z. So you see that when magnetic field goes to 0, magnetization goes to 0. So this is something which is known from the theory of paramagnetism. That is, paramagnetism only persists if there is a non-zero magnetic field. Magnetic field goes to 0, magnetization also goes to 0. All right. So now what we do is that we calculate the magnetic susceptibility. So we have to now sketch the zero field susceptibility and see how it varies at high and low temperatures. So this is what will basically give us Curie's law of paramagnetism. And this susceptibility will be known as Curie susceptibility. Okay, so chi of t is del m by del b at b equal to 0, zero field susceptibility. So if I take the derivative, b goes out from this expression and I have 2 mu naught square v by kBt lambda cube into f half of z. Also, you will see that I have to basically calculate the chi by the ratio of chi by n to verify Curie's law. Okay, so what is the value of capital N at b equal to 0? So for b not equal to 0, this was the value of capital N which I had. So n was n plus n minus into v by lambda cube of f plus 3 by 2 of this quantity plus f plus 3 by 2 this quantity. So in the limit of b going to 0, I replace these f3 by 2s by their Taylor expansion values. Okay. And then I arrive at this expression for n. That is, oh, sorry. actually at b equal to 0, this is equal to 1. So this is nothing but the summation of these two equal quantities. So n is equal to 2v by lambda cube into f3 by 2 of z. Okay. Now I have to find the zero field susceptibility in the two limits, that is at t going to 0 and t going to infinity. So as t goes to 0, we know that z goes to 0 and mu tends to epsilon f. So basically log z goes to minus infinity. All right. Oh, I'm sorry. As t goes to 0, actually log z goes to plus infinity and mu goes to epsilon f. All right. So fn of z, which was nothing but 1 by gamma n into integration of this quantity. So we had z inverse over here. I replaced the z inverse by e to the power of minus log z over here. Okay, so if I now look at this limit of log z going to infinity, then this is nothing but e to the power of minus infinity, which is 0. So this entire quantity becomes 1. So this is an integration from 0 to infinity. I replace infinity by log z over here. So this is 1 by gamma n 0 to log z integration dx x to the power n minus 1, which is 1 by n gamma n into log z to the power of n, right? So then for n equal to 3 by 2, which I had over here, n is capital N becomes nothing but 2v by lambda cube into 2 by 3 by 2 by 3 into 1 by gamma 3 by 2 ln z to the power of 3 by 2. So then log z is nothing but 3n root pi by 8v lambda cube raised to the power of 2 by 3. Okay, and if I do the same thing for the susceptibility over here, then chi is 2 mu naught square v by kbt lambda cube into 2 by root pi. 2 by root pi comes from this factor of n gamma n. So this is basically gamma half is equal to half and n is equal to half. So I have a factor of 2 over here into log z to the power of half. Okay, and if I substitute this value of log z over here, then chi becomes equal to this quantity. All right. So then this is chi over here and this is n over here. Okay. So if I take the ratio of the two, that is if I look at chi by n, then chi by n is nothing but mu naught square by kbt f half z by f3 by 2 of z. Okay. And f half z and f3 by 2z can be replaced by this expression in the limit of t going to 0. So what I get finally is that chi by n is nothing but 3 mu naught square by kbt into 1 by beta epsilon f, right? And since epsilon f is equal to kbtf, okay, so I can replace this thing in the limit of t going to 0 by this expression. All right, so in the limit of t going to 0, mm, chi by n approaches 3 mu naught square by 2 kbtf. Okay, so this t won't be here. This is actually a mistake over here. Right, so this t won't be here. So there will only be a kb over here, right? So this is chi by n is equal to 3 mu naught square by 2 kb into tf. Okay, so as t goes to 0, the zero field susceptibility retains a sort of a finite value, right? So that is what we see over here. So if I plot it on a graph of 1 by kb of chi by n mu naught square as a function of 1 by kbt. So in the limit of t going to 0, 1 by kbt approaches infinity. So as 1 by kbt approaches infinity, chi by n mu naught square, this tends to a constant value which is equal to 3 by 2 kbtf. Okay, so this is the result which we got over here. And in the limit of t going to infinity, that is when we have z going to 0, right? So as t goes to infinity, z goes to 0. So then fn z can be written in this particular formula manner. So then the z inverse e to the power x term becomes equal to 0. And we have, sorry, z in, yes, as z inverse e to the power x term becomes more important than the other term. So you have z coming out of the integral and you have e to the power minus x in the numerator over here. And this is nothing but gamma n. So fn z is nothing but equal to z. So if fnz is equal to z, then capital N is equal to 2v by lambda cube into z in this limit of t going to infinity. So then z becomes equal to n lambda cube by 2v, which goes to 0 as t goes to infinity because lambda goes to 0. Okay, and then you have this chi equal to 2 mu naught square v by kbt lambda cube into z. I replace z by this formula over here. So chi is equal to n mu naught square by kbt. So this is the celebrated Curie's law of paramagnetism. And this chi over here is known as Curie susceptibility. So this is how we are able to derive this Curie susceptibility from the properties of fermions itself. Okay. So if you look at this graph over here of 1 by kBt, so chi behaves linearly with respect to 1 by t in the limit of large T. So in the limit of large T, 1 by t goes to 0. So in this limit, you see chi is scaling linearly. So this is the Curie's law, and this is a zero temperature value, and this is the actual value which we have. So this actual value, it follows Curie's law at very high temperature. And as you go at lower temperatures, this value of susceptibility deviates from Curie's law and approaches a constant value. Okay, so now we look at this next problem, which is ferromagnetism. So what does this problem say? That the conduction electrons in a metal can be treated as a gas of spin half fermions. Okay, with up and down spin degeneracy and a density n equal to n by v. The Coulomb repulsion favors wave functions which are antisymmetric in position coordinates. So if antisymmetric in position coordinates means that you can't have two electrons in the same place because they'll be repelled by Coulomb repulsion. Thus, this keeps the electrons apart. And because of the full antisymmetry, that is the position and spin antisymmetry of fermionic wave functions, this interaction between fermions, so the interaction between two fermions can be approximated by an effective spin-spin coupling that favors states with parallel spins. So you know that electrons with opposite spins tend to stay closer to each other, and this tendency of staying closer to each other is something which opposes Coulomb repulsion. So there is an energy, so there is an instability in the system. So you have two competing interactions over here. So here the most stable state which can occur is that electrons are placed apart from each other and they are all having parallel spins. So this is the most energetically favored state, and this is stable state. So in order to achieve this stable state, there should be some interaction between the electrons, and this interaction between the electrons is described by this effective interaction energy, which is sort of like a potential energy. Okay. So U equal to alpha into n plus n minus by V denotes the interaction between the electrons in a conduction, between the conduction electrons in a metal. N plus and n minus are the number of electrons pointing with up spins and down spins with respect to a particular axis. And V is the total volume, and alpha is related to the scattering parameter, that is the scattering length small a, by this formula over here. Okay, and small m is the electron mass. So in the ground state, that is at t equal to 0, there are two Fermi-Cs which are filled up by the spin-up and spin-down electrons. Okay, so spin-up electrons have their own Fermi-C which is completely filled. Spin-down electrons also fill up their own Fermi-C. Okay, so we have to express the corresponding Fermi wave vectors in terms of the densities of the spin-down and spin-up electrons. So this is something which we had done earlier. So we are done for one for a given fermion gas. So this is nothing but two different fermion gases. One fermion gas consists of spin-ups, one fermion gas consists of spin-downs. And for them, the total number is given by this formula. And this can be written in terms of the Fermi wave vectors for the respective electrons in this manner. So the Fermi wave vectors for the spin-up and spin-down electrons, Kf plus minus, is equal to 6 pi square n plus minus to the power of 1/3, where n plus minus denotes the respective densities of the spin up and the spin down electrons. Now we have to calculate the kinetic energy of the ground state as a function of the densities and the other constants. So the yeah, for the energy of the electron with the wave number k is given by the kinetic energy is given by this formula, which we had seen earlier for free electrons, because in free electrons, the entire energy was kinetic energy because there was no potential. Okay, so the kinetic energy is h cross square k square by 2m. For the electrons which are occupied up to the Fermi level, we basically integrate this expression for the kinetic energies from 0 to kF plus minus, and then we get the total kinetic energies of the two sets of electrons in the ground state, right? So we get the kinetic energies of the ground states at the function of the electron densities. How do we do that? First, we get it in terms of kF plus minus. So the kinetic energy density is equal to E by V, which is h cross square by 2m, 1 by 10 pi square, kF plus to the power 5 plus kF minus to the power 5. And I have kF plus and kF minus given by this expression over here. If I replace that, then I get this expression for the total kinetic energy density of the system in the ground state. So these are for the upspin electrons in the ground state, and this term comes from the downspin electrons in the ground state. Now, how does the ferromagnetism arise in a system? It arises because of certain perturbations, and that's what we'll see now. So assume that there are now small deviations from this ground state. That is, there n plus is equal to n by 2 plus delta, and n minus 2 is equal to n by 2 minus delta. That means a delta fraction of electrons convert from upspin to a downspin. Okay. So suppose because of some instability, external or internal, there is a conversion of upspin and into downspin electrons. So the total number of upspin electron now becomes n by 2 plus delta, and the total number of downspin electrons is nothing but n by 2 minus delta. Initially both were n by 2. Now one increases and the other decreases by an order of magnitude equal to delta. Okay, so what is the question now? The question is that we have to now expand the kinetic energy in this state of asymmetry, in this perturbed state, up to fourth order in delta. So we look at the formula for binomial expansion. So if I have this quantity like x plus delta to the power of 5/3, then in the limit of small values of delta, I can do a binomial expansion. So this becomes x to the power of 5 by 3 plus 5 by 3 x to the power 2 by 3 into delta plus 10 by 9 x to the power minus 1/3 into delta square, and so on and so forth. So this is the expression of the binomial expansion in powers of delta and x. Now I basically replace instead of n plus in this expression, I write n plus n by 2 plus delta, and instead of n minus in this expression, I write n by 2 minus delta. Okay, so if I do that, and then I have a term like n by 2 plus delta to the power of 5/3 and n by 2 minus delta to the power of 5/3. Okay, so if I substitute n by 2 plus delta to the power 5/3 in this expression, and same for n minus, then I will get an expansion in terms of powers of delta. And since delta is a small quantity, I written terms up to only the fourth power in delta. So this becomes the total kinetic energy in this perturbed state. So in the perturbed state, the kinetic energy is nothing but h cross square by 2m, 6 by 5, 6 pi square to the power 2 by 3 prefactors, multiplied by n by 2 to the power of 5 by 3. This comes from the ground state contribution, plus 5 by 9 n by 2 to the power minus 1/3 delta square, plus 5 by 243 n by 2 to the power of minus 7 by 3 delta to the power 4, plus terms of the order of delta 6, and so on. So these other terms, these are the ones which are coming in because of the perturbation. Okay. So now I have to express the interaction density in terms of n and delta. So if I do that, then I will find that for certain values of alpha, the electron gas can lower its total energy by spontaneously developing a magnetization. Now you see, how does the magnetization develop in the system firstly? So because of this perturbation, you have certain downspin electrons converting to upspin electrons. So now they become imbalanced. So there is a net magnetic moment in the system. So because of this net magnetic moment, there is a magnetization. And this magnetization is proportional to delta. So larger value of delta, the greater is the magnetization which develops. And now we have to show that for certain values of alpha, the electron gas can lower its total energy by spontaneously developing a magnetization. Okay, so how does that happen? This happens pretty naturally. So we have this interaction energy, potential energy given by alpha into n plus into n minus by capital V. So this potential energy density is nothing but alpha into small n plus small n minus. So in the perturbed state, this is n by 2 plus delta, n minus 2 by 2, n by 2 minus delta. So this is equal to alpha n squared by 4 minus alpha delta square. So this is the contribution which comes in because of the perturbation. So the total energy density is the kinetic plus the potential energy. I can write it in this manner, okay? So this is the contribution to the total energy which comes in due to the unperturbed portion, okay? So E0 is basically the first term in this expansion over here. So E0 is given by this. This is the unperturbed part. And because of the perturbation, I have this term like this. Okay, so I have a term which goes like 4 by 3, 3 pi squared to the power 2 thirds into h cross squared by 2m into n minus 1 thirds minus alpha into delta square. So this delta square first coefficient is actually coming in from this term over here. And you have alpha which comes in from this term over here. Plus you have an order delta to the power of fourth term. And this order delta power 4 term is this term. And an important thing to note is that this order delta power 4 term is a positive term. Okay, so you see that if I have a value of alpha which is greater than this particular value, then the delta square term is a negative term. Okay, that means the system lowers its energy. I mean, system has a actually has a lower value of energy than it had earlier. So this was the energy which the system had earlier. Now, if my alpha is greater than this term over here, then the total energy is the initial unperturbed energy minus this energy, right? Because this term is anyway smaller than this term. So this energy is the total energy is this thing minus this energy. And this energy is actually a lower energy state, which means it is a more stable state. In other words, the system tends towards stability by lowering in its energy, and while lowering its energy, it gains magnetization. So, in other words, the system achieves stability by gaining spontaneous magnetization, and this is known as stoner ferromagnetism. This instability is known as stoner instability, which leads to spontaneous magnetization, and by gaining magnetization, it acquires a more stable energy state. So this is basically the origin of spontaneous magnetization in the system of fermions. And the spontaneous magnetization can only happen if the value of alpha is greater than this critical value of alpha c. Why? Because if alpha is less than alpha c, then you see that this term becomes positive. So this perturbed energy state actually has a higher value of energy, which is a less stable energy state. So in order to tend towards stability, the system will try to come back to the unperturbed state and it will lose its spontaneous magnetization. So this is the critical value of alpha above which we can have spontaneous magnetization and below which we won't. Okay, so now we have to explain qualitatively and sketch the behavior of spontaneous magnetization. So this stability of energy states which I was talking about, so this can also be graphically visualized from this graphs over here. Okay, so this graphs I have drawn by simply looking at this expression over here of the total energy. So this is the total energy density as a function of delta. This is delta equal to 0. So if alpha is less than alpha c, this term is a positive term, right? So then the total energy acquires its minimum value only when this term is delta is equal to 0. So it is like a parabola. Okay, it's a quadratic value, quadratic minima over here. Okay, so this is the minimum value which it achieves at delta equal to 0. So as I increase alpha continuously, then when my alpha becomes equal to alpha c, then what you see that this term vanishes entirely. And the first term is the fourth order term, which is a positive term. So I have a biquadratic minima over here. And as I increase alpha slightly beyond alpha c, what happens is that I develop a double well. How do I develop a double well? I have a negative value of a delta square here and a positive value of delta to the power 4 over here, right? So I develop a double well in this energy density graph. And you see the minima of this double well is actually the stable minima. I mean, these are lower than all the other energy values. So the system tends to acquire either of these two possible values of magnetization. So it can either have a positive magnetization or a negative magnetization, right? So this is what is known as spontaneous magnetization. So it can be n plus minus n minus or n minus minus n plus. Or in other words, if I plot a graph of magnetization as a function of alpha, you will see that below alpha equal to alpha c, magnetization is 0. And just beyond alpha c, it starts rising like this. And this curve is proportional to alpha minus alpha cy. The value of delta, the separation, is proportional to root over alpha minus alpha c. So that is why this curve scales like this. So in this way, we have both a qualitative and a quantitative view of how spontaneous magnetization can arise in a system of fermions, which are system of conduction electrons in a metal. Okay, and this is known as donor ferromagnetism. So going over to the next question on boson magnetism. So up till now, we had seen magnetism for fermions only. Now we take a look at magnetism for bosons. Okay. So consider a gas of non-interacting spin 1 bosons, each subject to a Hamiltonian of this particular form. Okay, so this is a Hamiltonian for bosons. A boson has symmetric wave function in both spin and space. So because of the symmetric wave function, the spin can take three values of -1, 0, and +1. Okay. Now, in a grand canonical ensemble of chemical potential, what are the average occupation numbers of one particle states? So this is something very simple which we have already done earlier. So average occupation number is nothing but 1 by e to the power beta into hs minus mu minus 1. Minus 1 because it's a boson, and this factor of hs gives me the energy of the system, right, as a function of spin. So average occupation number for spin s bosons is given by 1 by e to the power of beta into p squared by 2m minus mu naught sp minus beta mu minus 1. So depending on the values of s equal to 0, 1, and -1, it can have different occupation numbers, right? What is the total average total number of bosons with the three possible values of Sz in terms of the function f? Okay, so total number of bosons of a spin S is nothing but summation over energy levels Ns. And the summation can be replaced by an integration for a continuous system. So Ns is equal to V by 2 pi cube into 4 pi square into this integration. Now replace x by, I substitute x equal to beta h cross square k square by 2m over here. Basically, I have replaced p by h cross square over here. Okay, so I substitute x equal to beta h cross square k square by 2m over here. And then if I do the integrations, that is, I first do an integration by parts and then I try to express the remaining integral in terms of the f functions. Then what I get is that ns is equal to v by lambda cube into f3 by 2 z e to the power of beta mu naught sb. So for different values of s, I can have different values of capital Ns. Okay, and this is the f function for bosons over here. Now we have to write down an expression for magnetization by expanding the result for small magnetic field. I have to find the zero field susceptibility. So I have the magnetization given by mu naught into n plus minus n minus. So this is mu naught v by lambda cube. N plus is given by s equal to 1, n minus is given by s minus 1. So I have this expression from here. At small values of p, I again do a Taylor expansion of the f function over here like this, and I use the property that z into del z of f minus fm z is equal to fm minus 1 of z, same as what we had done earlier. So then I get this Taylor expanded value of f3 by 2. And now if I replace this in this particular expression over here, then I get m equal to 2 mu naught v by kbt lambda cube b into f half of z. So this is the same thing which I had obtained earlier as well for fermions. The only difference is that instead of F plus, I have F minus here because it's a boson. Okay. Now similarly for zero field susceptibility, I take derivative with respect to B and I obtain this expression for B going to 0. Okay. So in this way, I find the zero field susceptibility. For B equal to 0, now find the high temperature expansion for, now you have to find the value of susceptibility, where in terms of the number density and at any temperature T, and then we have to obtain the first quantum correction to the statistics of chi T at high temperatures. So basically, now we have to find the susceptibility at finite temperatures. So what do we do for that? So for that, we first take the limit of t going to infinity, and then we first find the correction to the t going to infinity limit of the susceptibility. And then if we expand into higher order terms, then we can obtain the susceptibility at any given temperature. So first, let us take a look at the t going to infinity limit of the system. So t going to infinity basically means z going to 0. So the total number density can be written in this manner: n plus n minus plus n0 by v. Okay, so n plus n minus and n0 can be read off from this formula over here. And for t going to infinity, you have and in the for b equal to 0, this term is equal to 0. So n plus n minus and n0 are all the same thing for b equal to 0. So small n is equal to nothing but 3 by lambda cube into f3 by 2 of z. So in the limit of z going to 0, f 3 by 2 can be expanded in the power series of the form that f3 by 2 of z is equal to z plus z squared by 2 to the power 3 by 2 plus z cube to the power of z cube divided by 3 to the power of 3 by 2 and so on. So then this becomes the expression for the number density. So since we have z going to 0, if I neglect these terms, then I obtain z is approximately equal to yeah, so if I replace these terms, then z is approximately equal to n lambda cube by 3, right? So now I invert, this expression for uh, invert this expression so as to express z in terms of n and lambda. So if I invert this expression, I get z is approximately equal to n lambda cube by 3 minus 1 by 2 to the power 3 by 2 n lambda cube by 3 whole square and so on, higher order terms. So we have in the limit of z going to 0, chi by n, chi was given over here. So chi by n is nothing but 2 mu naught divided by small n kbt lambda cube. Okay, so v by capital N is nothing but 1 by small n. So I have 2 mu naught by kbt small n into lambda cube into this term, that is f3 by 2. So f3 by 2 is z plus z squared by 2 to the power half. This was f half, I think, yes. So okay, so z plus z squared by 2 to the power half and so on. Okay, so now if I replace the value of z in this expression, then I get chi by n is equal to 2 mu naught squared by 3 kbt into 1 plus the higher order corrections. Okay, so this is 1 by 2 to the power half minus 1 by 2 to the power 3 by 2 n lambda cube by 3 plus other higher order terms of the order of n square and so on. So if I have the limit of t going to infinity, then I can neglect all these higher order terms. So then chi by n becomes equal to 2 mu naught squared by 3 kbt. So chi goes as 1 by t in the limit of t going to infinity, which is same as what we saw earlier for Curie susceptibility in case of fermions. Okay. Now we have to find the temperature of the Bose-Einstein condensation and what happens to susceptibility on approaching TC from the high temperature side. So in order to find the temperature for Bose-Einstein condensation, we have to basically find the value at which you have to basically put z equal to 1 in the expression for the number density. All right. And if you do that, you can find the expression for the critical temperature for Bose-Einstein condensation. So this is the critical temperature. Now, uh, for Bose-Einstein condensation, you have the limit of temperature approaching Tc. Basically, the Z approaches 1. And when Z approaches 1, you know that F half of Z, it diverges. Right, and if F half of 1 diverges, then susceptibility will diverge. So as we approach the critical temperature from the high temperature side, the susceptibility diverges. So this is what happens. And what is the expression for chemical potential for T less than the critical temperature at small but finite value of B, and which state has the maximum occupation number? So you know that the chemical potential for bosons is always negative. And if I look at this expression, f of this thing becomes equal to 1. That means that z equal to z into e to the power beta mu naught sp is equal to 1. So mu is equal to minus mu naught sp, and this is negative only when s is equal to 1. So the value of chemical potential for T less than Tc is nothing but mu naught into B. And the state with the highest occupation is equal to K equal to 0 and S equal to 1. Because for this state, if you see, the average occupation number goes to infinity. So this is the state with macroscopic occupation. And using this result, we have to find the spontaneous magnetization. So the spontaneous magnetization is given nothing but the magnetization in the limit of zero field. Now, an important thing to note over here is that in case of fermions, we never had any spontaneous magnetization. It was all paramagnetism. Only if the fermions were free fermions, then we had the spontaneous magnetization, which gave rise to ferromagnetism. Okay, now let us see how this spontaneous magnetization arises in case of Bose-Einstein condensation. So sorry, how this arises in case of a system of bosons. Okay, so as the magnetic field goes to zero, the contribution of the excited states to the magnetization vanishes, right? Because as the magnetic field goes to zero, the contribution of the excited state vanishes because magnetic expression. If you look at the expression for magnetization over here, M is proportional to B for the excited states, right? So if B goes to 0, then M will also go to 0. So the contribution from the excited states to the magnetization goes to 0. Thus, the contribution to the spontaneous magnetization only comes from those states which occupy the lowest energy level. That means it comes from the condensate itself. That is the ones which occupy particles which occupy the state k equal to 0 and s at equal to 1. Therefore, for a bosonic system, the spontaneous magnetization occurs at T less than Tc. So the spontaneous magnetization is given by mu naught of G into n plus, right? Where n plus is all these electrons which occupy the lowest energy state. Basically, mu naught into total number of electrons which occupy the lowest energy state. That means the total number of not electrons, total number of particles which are a part of the condensate. So this is nothing but mu naught phi into total number of particles minus the number of excited particles. And the number of excited particles at T below Tc, it saturates to this particular value, which is obtained by setting this obtained from this particular expression over here. So then the spontaneous magnetization is mu naught into n minus 3v by lambda cube into zeta 3 by 2. So this is the expression for spontaneous magnetization for T less than Tc, and it only comes from the from the particles which are there in the condensate. Okay, so far we have only done non-relativistic gases. So now we turn to the example of a relativistic Bose gas in d dimensions. So now we consider a gas of non-interacting spinless bosons with energy epsilon equal to C into mod P contained in a box of volume V. And we have to calculate first the grand potential and the number density. Okay. So this is the energy of in the relativistic boson. So this is the expression for grand partition function which we had earlier, right? And I've written this in terms of the energies of the individual levels. And this, if I remove the constraint on the total particle number, then this can be written in terms of this product over the energy levels 1 by 1 minus e to the power beta into mu minus epsilon I. So the log of this quantity is nothing but minus summation I log of this quantity. Okay, so I now replace the summation by the integral, and I set epsilon equal to Cp, P is equal to H cross K. So epsilon is nothing but Ch cross K. K is a wave number, and I am working in d-dimensional space. So I have this factor of St into k to the power d minus 1 into dk over here. So this is the expression for log of Q. Now I replace x by beta H cross K. So then dk becomes equal to dx by beta H cross C. If I do this substitution, then basically log of Q is equal to nothing but minus phi into St by 2 pi raised to the power of t, kbt by H cross C raised to the power of d, 0 to infinity, dx into x to the power d minus 1 log of 1 minus z e to the power minus x. Okay, so now what I do is that I do an integration by parts. So if I do an integration by parts, this term becomes x to the power d. The first term vanishes out, and this is the second term which I get. So these are the factors which I had outside the integral. 1 by d comes from the integration of x to the power d minus 1. And this is the term which I have inside the integrand. Okay, so if I divide by z e to the power minus x, both the numerator and denominator, then I arrive at this expression. And this is nothing but f of d plus 1 into gamma d plus 1. Minus sign denotes a boson. Okay, so then the grand potential can be written as minus kbt ln q. So this is nothing but Vst by 2 pi to the power of t 1 by d kbt coming from here, kbt by h cross c to the power d, d factorial f minus d plus 1 of z. Okay, d factorial is basically gamma of d plus 1. That is d factorial if I consider d to be only integer values. Now I replace lambda c, I make the substitution that lambda c equal to hc by kbt. And I also replace the value of st in this integral, in this expression, and then I arrive at this expression for the grand potential, which is minus kbt v by lambda c to the power of d pi to the power of d by 2 divided by d by 2 factorial into d factorial into f d plus 1 of z. So then the total number of particles n is equal to z into del del z of log q. Now log q is nothing but zeta into minus beta into zeta, right? So if I place that, then this is nothing but beta into z del del z of zeta. If I take the del del z of this expression, I get n is equal to v by lambda c to the power d pi to the power d by 2 by d by 2 factorial into d by 2. So this beta cancels out this kbt, and this is f d minus of z. And this expression is the expression for number density. Now I have to calculate the gas pressure, its energy, and compare the ratio E by PV to the classical value. So beta PV is equal to ln Q, which implies that PV is equal to minus zeta. Okay, and E is equal to minus del del beta of log Q at a given Z. So then this is nothing but d by beta into log Q if we do the calculations, which is equal to minus d zeta. And therefore E by PV is equal to D. And if you compare it with the classical value, it was different. So PV by E in case of earlier we had S by D. Here we have only 1 by D. So S is equal to 1 over here. Okay. But now we have to find the critical temperature for Bose-Einstein condensation, indicating the dimension where there is a transition. So for Bose-Einstein condensation, I basically have to replace Z over here by 1. And then I have to find the critical temperature. So this becomes the expression for the critical temperature for Bose-Einstein condensation. And you see that this critical, there will be a Bose-Einstein condensation if Tc has a finite value. And Tc has a finite value only if zeta d is finite. Okay, zeta d is finite only when d is greater than 1. So for a relativistic Bose gas, Bose-Einstein condensation occurs for all d greater than 1. So earlier we had seen for the non-relativistic Bose gas, it can only occur when the critical dimension is greater than 2. And for a relativistic Bose gas, it is possible for Bose-Einstein condensation to take place in d equal to two dimensions as well. However, in d equal to 1 dimension, it's not possible. What is the temperature dependence of the heat capacity for a temperature less than the critical temperature? So for T less and Tc, we basically put Z equal to 1 in the expression, all the expressions that we have. So the internal energy is nothing but d into zeta. Okay, so minus d zeta is equal to this expression where we have put Z equal to 1. And you will see that this is proportional to t to the power of d plus 1. So if I calculate the specific heat, then I have to take the derivative with respect to temperature. So this becomes d plus 1, which comes from this factor over here, into E by T. Okay, why? Because E is proportional to T to the D by D plus 1, and this is proportional to T to the power T. So that is why E by T. And this is nothing but equal to minus D into D plus 1 zeta by T, because E is equal to minus D zeta. All right. So if I replace that expression of zeta, I get this huge expression over here. So what I get is that the specific heat is proportional to T to the power D for T less than Tc for a relativistic Bose gas. And now at the critical temperature, what is the dimensionless heat capacity? So at T equal to Tc, the dimensionless heat capacity is basically C by N kb. I know C, I have to now find out N. I had N over here in this expression over here. So if I put Z equal to 1, then this is the expression of N which I have at T equal to Tc, and Ft of 1 is nothing but zeta d. So the dimensionless heat capacity C by N kb is obtained if I take the ratio of C and N kb, and this turns out to be equal to D into D plus 1, zeta d plus 1 by zeta d. And for the classical ideal gas, it is a non-relativistic gas, it is a D in the high temperature limit. Okay, so yeah, so that is all. So these are the 5 problems which I had for today's class. The next class, we'll also continue with the discussions after this. Okay. So in the next class, we'll probably discuss Chandrasekhar limit and black body radiation. And we'll also discuss problems if we have time. So that's all.